Good morning, physical science students, and welcome to week 13. Today, we're starting actually a different kind of topic, namely, we're getting into the chemistry part of our class. It's really a boundary between chemistry and physics because this is still atomic physics. So it's still based on the mechanics that describe basically different motions involved in this case. So let me get into it, okay? Albeit it's a different kind of mechanics called quantum mechanics, because once we are on this level of extremely small particles, extremely small elementary particles, classical mechanics, namely F equals to ma, Newton's law of motion, does not apply anymore. So we have to apply a new branch of physics. So, and let me get into it and let me explain basically. Let me share the screen first. Find it. Here is the share button. And let me pull the screen. I know it shows something else right now, but let me switch directly to it. So again, we are in week 13, and I'm going to get a little bit into the objective in here because I want you guys to remember that we have quite a few stuff that is still due this week. So we have a lot of things that are due on top of another item that popped up this week, and that is a survey. So we still have homework. We still have several discussions now. Two of them are due on the same date, and we delayed it because of the exam. We still have another exam that is coming, so we need to get ready for it too. And that exam is most likely going to happen immediately after the holiday break, after Thanksgiving break. So you really need to be ready for it. In addition, we have these two surveys. Unfortunately, at this point, I did not hear from you in terms of the last survey, but this is an important survey. Please turn it as soon as possible. The topics of this week deal with the periodic table, and we're going to deal with the properties of the atom basically and the elements, and also understand where these properties are coming from. Let me get into the next component of this week's module. Again, it deals with the periodic table. This is something that you're into whenever you go to a chemistry lab. You will see that. It's also in a lot of physics labs. So it's probably in biology too. So it's everywhere. The atom is an old concept. This is something that we have had for a long, long time. People thought that if we take matter and keep on dividing it, the smallest amount of matter that cannot be divided is what is atom. This is the smallest thing that makes up an element. For example, gold, if I keep on cutting it, at some point I will arrive to whatever makes that gold, which is the atom of the gold in this case. So there is a distinction between an element and the atom. The atom is actually a specific part of the element. The element is the entire picture. Anyway, sometimes we use them exchangeably. Okay. What makes up the atom is three particles. A proton and neutron reside in the nucleus, and then you have electrons outside of the nucleus. The proton and the electron are charged. One of them is negatively charged and the other one is positively charged. And the neutron is neutral, does not have a charge. The neutral does not interact in the electrostatic force. In other words, it does not attract or repel protons or electrons for that matter. It's neutral, it doesn't have a charge. But it participates in the nuclear force in a sense that it interacts with the proton and actually binds with them. As a matter of fact, it's a very strong attractive force, as opposed to the electrostatic force, which can or cannot be attractive depending on the sign of the charges. The nuclear force in here inside the nucleus is actually an attractive force. So actually neutrons are important in terms of the stability of the atoms. So this is in general basically the idea. Some of the concepts that you need to be familiar with are the atomic number, which is basically how many protons are inside the nucleus. If the atom is neutral, that is also the number of the electrons. If the atom is not neutral, is ionized, for example, it gained an electron or two or three, then the numbers of the protons and the electrons are not balanced. Or same fashion, if it loses one electron or two or three. So in that case, it becomes positively charged and so on and so forth. Okay. Isotopes is what distinguishes, it's the same element. For example, oxygen 15 and oxygen 12, they're both oxygen. Carbon 14 and carbon 12, they're both carbon. But one of them is heavier than the other, that's all. One of them has more neutrons than the other. Carbon 14 has 2 neutrons in addition to the 6 neutrons, for a total of 8 neutrons, plus the 6 protons. That makes it 14 nucleons. We call them nucleons. Protons and neutrons, they have a name, which is nucleons, okay? So you have 14 in this case. Carbon is heavier than the normal carbon, which is 12, which has 6 protons and 6 neutrons also only. So this is the distinction between them, which brings me to the concept of the atomic mass in here. And basically what the atomic mass is the number of nucleons multiplied by this basic unit in here, which is the AMU, 1 atomic mass unit, okay? Which is a very tiny number, as you can tell. That's the mass of a proton, if you wish, or that of a neutron, which are extremely heavy as compared to that of an electron, okay? Almost 2 times heavier than the electron, okay? Again, the periodic table is something that you have seen. It characterizes by 2 concepts in here that you really have to understand. First of all, the groups. This what makes the chemical properties. This what chemists are interested in when it comes to chemistry. Which group that element is, with the exception of the hydrogen, which has its own behavior when it comes to chemistry. Almost all of the other elements have similar behavior as long as they're in the same group, because that is the number of electrons in the outer shells that participate in the chemical bonding. So as chemists, this is what really interests us. This is another one. This has 1 electron that can play: lithium, sodium, potassium, so on and so forth. Beryllium, on the other hand, and manganese, calcium, and strontium, and all of the other elements, they have 2. And then I have this group in here, which has its own behavior. And then you have boron, aluminum, and so on and so forth, carbon, silicon, germanium, and nitrogen, phosphorus, arsenic, and so on and so forth, oxygen, and the rest of the elements, basically. These are neutral, okay? These are neutral elements. They don't do anything. These are called they are inert in a sense. They don't participate in any chemical bonding, okay? Probably under extreme temperature, extreme pressures, they may do something once they become ionized, but they are chemically neutral, okay? So this is in terms of groups. In terms of periods, basically, and we will see that briefly, you have also this period 1, 2, and so on and so forth. That's why it's called periodic table, actually, okay, because of this cyclic properties. That's when Mendeleev basically discovered that there is a pattern in here in all of these things. Now, let me get into a little bit. So the elements are all represented in the periodic table. They occur in nature in about 90 of them, and the rest of them, they are man-made, basically, okay? So in terms of namings, those are the alkali. Sometimes oxygen is, hydrogen is included with them, but like I said, hydrogen can behave both as a donor and also as a receiver, as an acceptor. So it's an exception, okay? The rest are alkali. Then you have the alkalines or earth metals. That's how they are known. You have the transition metals in here, which behave for the most part as metals. Now, for those of you sitting in the astronomy class, anything other than hydrogen is called a metal. That's of course not correct in the sense of chemistry and physics. Metals, they basically tend to when they come into a chemical bonding, they actually give that extra electrons that they have, whereas the non-metals in this case, especially the halogens that most of the time interact with them, they take that extra oxygen because they have a very big affinity for the electrons in this case. So you have the halogens and you have the noble gases. The noble gases, they don't really participate in any chemical bonding. These ones, they don't have any kind of name. So they're carbon and silicon and germanium and all the other elements in here. Sometimes the oxygen and the group in here, they're called calogens. I think that's how they're called. Anyway, the point being in here is we're not really interested in the namings. We're not interested in even the names of the elements. All we are interested in is actually the patterns in general. And that is the main thing when it comes to chemistry. Chemists really takes this table and tries to identify the properties just by looking at it. Some of the information listed in here is actually the atomic masses in here, okay? So, not the, I'm sorry, not the atomic mass, the atomic number in here is given, mainly how many electrons it has, or how many protons it has. This has 1, this has 2. Of course, this has 4 atomic masses, because it has 2 protons and 2 neutrons, and so on and so forth. Depending on the specific isotope, some periodic tables, they give you the atomic mass, okay? When they do, because I mentioned already the isotopes, you have an average value in there. That's why they're not exact. So if you look at the oxygen, you're not gonna see it exactly 16, albeit you have 8 protons and 8 neutrons in a specific in an atom, which is typically of the oxygen, the main isotope, but sometimes it's less than that, it's 15. So they give you an average in here, and the number you will see for the atomic mass is slightly less than 16, and so on and so forth. And this is true for all of the other elements, depending on the number of isotopes and their frequency, which one is the main dominant one, and the ones that are less and less, and how much proportionally they are. So there is a lot of information in the periodic table. In addition to the chemical properties, you also have the physical properties, okay? Each element, it turns out, when we were experimenting with them, they have a specific signature, okay? They have a specific, if you excite them, for example, you heat an element like this, and then you watch its spectrum that is emitted. So this is an emission spectrum in this case. Each element, depending on what we're dealing with, if it's strontium, potassium, barium, or copper, you will see that it has unique lines. So if you see this line with this one, you know exactly what you're dealing with. This is copper, this is strontium, so on and so forth. It has all of this one. This is in the visible range. In the infrared range on this side, or the ultraviolet range on this side, you also may have some lines, okay? So you need special detectors for that, but you can find them for the UV range, or higher than the violet range and lower than the red range, and so on and so forth. Okay, so this is specific, indicating that somehow the energy levels where these things are, because we excited the element, and now the element all of a sudden is getting rid of that excess energy because it's getting its temperature less and less. So it's really going back and settling down to a ground energy level. So in this case, it's emitting them, but it's also emitting them specifically in certain values. Okay, this is where the quantization came from. This is where the idea that we know that the atom somehow is quantized. Okay, the energy levels in the atom are somehow quantized, and that's where quantum mechanics came into play. It started, actually, the idea started with a hypothesis that Mr. Planck made for the, and I know I mentioned that before, the black body radiation. It turns out that the energy levels in this case, if we did not count for them being quantized, they would lead to the ultraviolet catastrophe that I mentioned in the past. So in order to avert that, he introduced the idea that the energy levels for the case, in that case, for the excited states in the case of the black body must be in discrete fashion quantized. Then Mr. Einstein took that same idea and actually explained the photoelectric effect, which led later on to basically that's the concept of the photon that was introduced. It turns out the energy in this case is proportional to the frequency, because what we're dealing with in this case is emitted light. And the energy levels and the frequency in this case turn out to be proportional. The higher the frequency for the case of the violet, the higher the energy transition. So you're dealing with a high transition level. Whereas in the case of the red one, you're dealing with a short transition, okay? Because in that case, the wavelength is longer, and the energy level is closer to one another. The frequency is less and less, okay? So that is the idea behind it. And the constant of proportionality is actually what Mr. Planck has introduced, a constant H, which turned out to be 6.626 times 10 to the negative 34 joules times second. So that is the Planck's constant. So Mr. Niels Bohr took that idea and he made a hypothesis that actually the angular momentum is actually quantized. And he was able to explain beautifully this transitions for the case of the hydrogen atom or the hydrogen-like atoms. Okay, so again, we're going through the idea of a model to model to model. Now, initially, actually, and I really didn't want to go in detail about this one because I really want you guys to read about these things, is that we thought that the atom is somehow, it's like a dough of a cookie dough, for example, that has the chips inside spread around. Those chips, they represent the electrons because we know the electrons exist because electricity, and we know the atom is neutral. So there must be an amount of charge that is positive to cancel those electrons. So think of the dough as being the positive charge, which is like a mixture of charges positive. And then you have the chips, the chocolate chips in this case, that are spread around, which would represent the electrons. Well, that model was actually, so that's the idea. We introduced an idea to explain something, but then we had to check it. When we checked it with the Rutherford experiment, when he threw the alpha particles, which are nothing but the hydrogen, the helium atoms with stripped out of their electrons. So these elements in here that come from radioactivity, radioactive material produce alpha particles, which turn out to be just the helium atom without its electrons. So we know it's positively charged as it goes through those materials. For the most part, goes unimpeded. So that model basically does not work anymore because the atom is mainly empty. As a matter of fact, only a handful of them bounce back, which indicates that the nucleus is tiny. And for the picture that we have for the dough and the chocolate chips is wrong then. We had to fix it in a sense that the electrons must exist on a shell outside and the nucleus inside. Well, that model did not work either, because we know from classical mechanics that the electrons, as they move, they need to be accelerated because of centripetal acceleration, centripetal acceleration. Any charge that is accelerating will emit light. So they will lose energy and they will collapse on the atom, and the atom should not exist. If the atom doesn't exist, nobody exists. And we know we exist, we know the atoms exist. So this picture is wrong too. So we needed to fix that. That's when Mr. Bohr came in and took the ideas that Mr. Planck and Einstein introduced and introduced the quantization of the energy for the atom. And he said that the angular momentum is quantized, and he came up with the different energy levels. And that model now looks a little bit stronger, actually works beautifully for the hydrogen atom, this element. But he tried very hard to extend it to the other elements, and he couldn't, unless the other element behaves like hydrogen. Basically take the helium and take at least one of its electrons, and now it's like hydrogen anymore. Same thing, except it's an ionized helium. Same thing with lithium, take 2 electrons off of it and just leave 1. But then that model actually needed to be corrected, and that's where modern quantum mechanics came into play and gave us this picture, the shell structure of the idea that we know of. So different energy levels from n equals to 1, 2, and so on and so forth. You have 2 electrons in the first level, n equals to 1, 8 electrons in the second one, 8 in the third one, 18 in the third one. These are the so-called S, P, D, F levels, okay? Now, that is where the groups, that is where the periods are coming from. Period 1 is actually only 1 energy level in this case, n equals to 1. Not the fundamental energy level where the 2 electrons can exist. There is another principle in here that comes into, because the electrons have a spin 1/2, they cannot exist in the same energy levels. So one of them, for the case of helium, must be up, the other one must be down, because they cannot exist both in the same energy level by another principle Mr. Pauli discovered. For the group, for the period n equals to 2, you have this much. And for the period n equals to 3, and so on and so forth. That's basically how you can look back into the periodic table and understand what's going on with it. Okay, this went too fast in here, sorry. Okay, So again, here are the period 1, 2, and so on and so forth. And these are the groups. The groups in here have to do with the electrons. This is in a nutshell your chapter. I may have to come back to it later on, and we may have to have extra discussions about it. So we'll see. The discussion items are in here. The recording of this video will be posted in here, and you have some helpful videos that hopefully you can watch. And as you go along with the discussions, and again, this is the PowerPoint that I typically submit for you guys, and you have the survey. Please take the survey. And as I was saying, you will have an exam immediately. So you have the review before the spring break, and you will have the actual exam immediately after the spring break. Spring break. I'm sorry. Why am I talking about? Thanksgiving break. Thank you very much. Let me stop sharing. And if you guys have any question, please don't hesitate to send it. Thank you.